Thank you very much, first of all, to the organizers of Danger. It's a great pleasure to speak to this audience because I know this is a place where, let's say, the most mathematical point of view of machine learning and artificial intelligence is taking place. And everything I'm going to present is subsets of joint work with several people that are mentioned here. So there's several papers. I think all of them are published by now. So I will take pieces from several of these papers, and you can find all of them in the archive. So what's the message? And I think this message maybe, again, is maybe not necessary to this audience, but the message here is the discrete geometry matters a lot for data science and artificial intelligence and statistics. I believe that this applies, as we saw in the previous talk by Henry, that every area of mathematics really has something to contribute to the development of data science. And if I have time a little bit at the end, I will comment that there is also true in the other direction. So data science, we can think of mathematics as a science that generates data. And therefore, we can also analyze the data coming from geometry and algebra, other areas. And I'll mention a few things at the end if there's time. Anyway, so my plan is to tell you how two very important theorems in convex geometry, in discrete convex geometry, are actually very relevant to data science and statistical inference. And I will just finish with some conclusions, and feel free, please, to interrupt me. I cannot see the chat. I'm unable to follow the chat and follow the talk. So if somebody can help me, if there's a question, just unmute yourself, or please tell me there's a question in the chat and read it to me. Okay, so the first, let me start with something kind of innocent looking. So you have data, and as you can see here, there's two pictures of red and blue data. And data, in some senses, we can think of it very geometrically in the sense that we like in discrete geometry, which is a collection of a cloud of points, a collection of points. And the classification problems, to some extent, are just separation problems of the data, right? So if I want to say, you know, Republicans and Democrats, or good people, bad people, whatever, you want to separate them and you want to classify them. And clearly the data on the left, there's a line that separates the data. So it's linearly separable. So there's a degree 1 polynomial that separates the data. And then but the other one next to it on the right is not possible. So there's a very natural question that let's just start as a warm-up of the kinds of questions that I'm interested here is when is data linearly separable to begin with? You know, is there some condition that one can say, in fact, that one condition that one can check to some extent, right? And it turns out that there's a very old theorem, I mean, at least from the 1900s. So this theorem is Kirchberger theorem that says that if you have data, blue points, red points, so I'm just talking about two colors for now, you can separate it if you can check this, you can separate linearly. What you can do is take every subset of d plus 1 points of the data. So you take a sample of d plus 2 points, and you can separate those d plus 2 points with a line, and you can do this every time. Then the data is strictly separable by a plane. This is a very nice condition, and let's look at an example here. So let's look at this this data that you see here that you cannot separate by a line. Well, we can see that, for example, let's see, these 3 points, these three blue points that can you see my cursor, by the way? If I mark three points here, these 2 blue points, yes. This third blue point, and then let's take this red point in the middle. So it's like a triangle of blue points, and then there's a red point. And this cannot be separated by a line, right? I mean, there's no way, because if you put a line, you always leave, you know, a blue point on one side. I mean, a red point and a blue point on one side of the line. So that's not separable. So in any case, so this is, and also you can think of this as there's a sufficient sample where, you know, in this case, if there is no separability, you can find kind of a minimal counterexample of linear separability. And of course, yeah, so let me say, by the way, I'm just here starting with linear separable, but obviously I can generalize to degree K separable, right? So there's exactly the same theorem. I didn't state this theorem, but what happens is that then you have to look at larger samples of points, right? So you have to look at points essentially by the Veronese embedding. I know that there's several people here that will understand what I mean by the Veronese embedding. You can actually transfer this condition to quadratic equations or to cubic equations or whatever, right? So there's some condition here of separability on any degree. And we know that the more we sample and we see separability, we start to believe that there has to be separability of degree K, right? So that's one application of already a theorem of Kirchberger. We will see the Kirchberger is a special case of an even more general theorem that is coming up. Let me show you another example of separability or classification. This is the question of median. So in the median, you have a list of points, so numbers. I mean, in the statistics that we teach undergraduate students, we have a list of numbers, and we want to find the one in the middle, right? And you know, the median is very nice because it's more descriptive than the average very often. And anyway, so in 1975, the famous statistician Tocchi started thinking about, is there a generalization of the notion of median for high dimensional data? Is there a notion that we can actually find a point in the data that represents, is more or less in the middle of the data, right? So what is that? And so he introduced a notion of depth of data. So if you have a data point or a point in a data cloud, P, I'm going to say that this point has depth or half space depth K. Can you see here? Oh, sorry. Yeah, that if every hyperplane that passes through my point P is going to contain at least K points in each side, at least K points of the data set. Okay, so then you can define what will be the center point, what will be the analog of the median, as it's a point that has depth at least n divided by d plus 1. Okay, and so this is a point that is very centrally located inside the data set. And I mean, if you're trying to find a sample that is very representative or is in the middle of the sample, this is the point that you would like to find, right? But the question is, how do you find this point, right? How do you find this point? So Tocchi proved that this exists, and the original proof by Tocchi used the fixed point theorems. I mean, the Brouwer fixed point theorems, right? So this non-trivial fixed point theorems in topology. And so just so that you understand what I'm talking about, so let's see. So in general, you have n divided by d plus 1, right? So if you are in dimension 2, so if you, but this can be generalized for not just data clouds. When you have data clouds, when you take the limit, you're looking at measures, right? You can have a measure. So in this case, I don't know in England or in Britain how they call this little guy that I'm showing here. This is Tweety in the US, I guess. And Tweety. Yeah, so this is this little bird. There exists a point that I can trace, that I can find inside this picture in such a way that I leave at least 1/3 of the area in each side of Tweety, right? So I can find this point. Now, of course, again, finding the center point is very difficult, and people are interested in finding algorithms. For example, randomized algorithms is one thing that people do. And you will see that some of the things that I'm interested in, so approximate the center point of the data, right? So that's another thing. And now it turns out that to connect it to the previous application that I show you, yeah. So this theorem is another application of a very famous theorem that is coming up. Let me tell you another application. So suppose you have points of data that are coming from a distribution that you don't know the distribution. Okay, these points, imagine the blue points are coming from some distribution of the data that is not given to you. You don't know it. but your challenge is to find the smallest ball of radius, you know, the smallest radius ball that you can contain a large proportion of the points. So the way that I always like to think about this problem is, imagine that the blue points is a tumor, is cancer, right? You want to remove 90% of the cancer by some surgical removal of this cancer. So you would like to remove, let's say, 93% of the points, or 93% of the measure, of the volume of this measure. Yeah, this probability measure. And so the question is, how do you solve this problem, right? So actually, in optimization, I mean, there's a formulation of this problem, a very natural formulation of this problem, that is a stochastic optimization. So in the sense of a stochastic optimization, we know that this can be formulated as, well, we want to find the radius, and this time the radius, I call it xd plus 1, so it's the last coordinate. And I want the distance of the points, you know, of course, my center of the center point of my circle has coordinates, you know, x2, x3, etc. So these are the other coordinates of the point that I'm looking for. And I want to prove that the probability that the distance is less than xd plus 1 is at least 1 minus epsilon. So there's an error. You're willing to tolerate a fraction, let's say 1/3, 1/4, or 0.7 or something, that you fail to satisfy this condition. So there's a tolerance error, and this is very important in applications, because we have a risk, right? We are tolerating some risk. So of course, in cancer, maybe you want to put epsilon very small, right? Epsilon, you want it to be very, very small, because that's in some sense the failure that you want to have. You don't want to fail, but maybe in other situations, the failure can be larger, right? So how do people solve this problem? And this goes back to the idea that I was trying to propose to you already. You want to find sufficiently many samples. You want to sample enough of the blue points. You want to sample enough from this distribution in order for you to be sure that with sufficient samples, you're going to get a good quality of prediction. Okay? Is the problem clear? So you are willing to tolerate some risk of failure, but you don't want it to be too much. You want to control it. Okay? So how do you do that? Okay? So let me just go directly to the theorem. So this is a theorem that actually has many forms, but this theorem was first proposed by Calafiori and Campi in 2000, what was it, 2010, I believe, or 2008. So what they say is the following. So why don't we sample from this distribution? You know, we take n samples, and if you take n samples, then you can solve a deterministic problem, right? So now you have a problem for the particular sampling data that you did. You want to find the smallest circle or the smallest disk that contains this data. Okay, but now it's deterministic because you sample n points. Okay, so the question is, well, how good is your approximation going to be to the true probability distribution that you are trying to approximate? You are making approximation, and again, so you have the parameter epsilon, which is the tolerance, but you want to be sure of your let's say of your result. I mean, you want to be sure. Okay, you say I'm sampling and I'm getting removal of 93% of the cancer, but I'm, let's say, 50% sure or 70% sure. That's this parameter delta that you see there. Okay, and so then the theorem is the following. So if you look at this beauty, I mean, to me, it's incredible. I mean, you have a bound on the sample. If you sample these many points, you are going to be actually sure that this problem, I mean, you have some guarantee that this problem will be giving you a feasible optimal, well, a feasible solution with some guarantee of optimality. And this is the number of samples that you have to take. So clearly the number of samples, it has to grow with epsilon, right? Because if you want to be more sure, you have to sample more. And also it grows with delta, same reason, right? You want to be more sure, well, then you have to sample more. But I will show you here, there's an interesting parameter. It's just the dimension, it's linear in the dimension. And so we have generalized this theorem to other situations where, for example, the points, you're not sampling real value points, but you're sampling integer value points in some situations, because you need to have integer solutions. In your application, sometimes you need to have integer solutions. And so the message is that sampling can give you great information about a large problem that you don't know enough. Like in the case of separability, you sample many times and you separate with lines, so then you can start to feel sure that you can separate with a line. Okay, are you with me so far? Any questions or reactions so far? Let me just stop here for a sec. All right, so where are these, all these theorems come from one main ingredient. So that's kind of the message here. Behind all these examples that I gave you, you have one theorem, a beautiful theorem in discrete geometry called Helly's theorem. So Helly's theorem says that if you have a finite family of convex sets in dimension D, and you tell me that every D plus one of them have a common point of intersection, then all the family intersects. There's a non-empty intersection of these points. So Helly's theorem has become a way to sample, to predict sample size on data science. I mean, on many questions of this kind that I was showing you before. So for example, the Kirchberger theorem that I show you about separability of data is a consequence. You can prove it using Helly's theorem, right? So it's a consequence with Helly's theorem. And not only that, I mean, you can also prove variations of Helly's theorem that give you new generalizations of Kirchberger theorem. Again, I mentioned already the variations with integer data. So when you are forced that the data needs to be integer. For example, there are situations where the values of the data have to be integer, like the number of people that were registered yesterday for the class or something. So it has an integer number, right? So that's the kind of thing. Okay, but okay, let me now show you another example of applications where discrete geometry plays a very interesting role, maybe a little bit unexpected role. And that is, there's a new theorem. Well, it's not so new. It's more recent than Kirchberger for sure. Oops, how do I move this? Oh wait, there you are. So the theorem is Erberg's theorem. So let me, for those of you that have never heard of Erberg's theorem, let me tell you what it says. So again, you have a lot of points. This is, think of what A1, A2, AN. This is your data set, right? So you have some points. And this time I have to classify my points into M different types, you know, maybe dogs, cats, I don't know, elephants. I mean, there's different categories or different types of data, right? Now, okay, here's what this theorem says. It says that if you have a lot of points, if you have sufficiently many sample points, so in this case, the number of sample points is bigger than the dimension of the points plus times the number of types minus 1, then you can always, every single time, you can partition the data into M. Okay, can you hear me? Oh. Okay, can you still hear me? Because I know that my camera somehow switch off.
Yeah, we can still hear you. And actually, okay, just now we can see you again.
Okay. Yeah, so yeah. So if you, again, so the message is, if you have sufficiently many points, if the number of points is bigger than D plus 1 times M minus 1, then you can partition the points into M classes such that the convex holes intersect. The convex holes intersect. So here's an example here in dimension 2. And in this case, there's only two color classes. M is equal to 2. So in the left, you see here. So what does the theorem says? If you have more than more than d plus 2 points or more, so that you have at least d plus 2 points, right? Because m is equal to 2 in this example. Then you will always be able to partition the points into green points and red points in such a way that the convex hull of the red points and the convex hull of the green points intersect. Okay, and then here is another example, again in dimension 2, but this time m is equal to 3. So what does the theorem says? It says that if you have 7 points, or at least 7 points, which is the case, then I will always be able to partition the family of points into 3 colors, such that the red, the green, and the blue color intersect on the convex hull. So is the theorem clear? This theorem is going to be very important, in a few moments for many applications. Are you with me? So that's a very nice theorem. And again, so there are, if you are a computational mathematician, or if you want to do applications, you wonder how, okay, that's great, that's a very nice theorem, but how do I find this partition, right? I mean, it's a natural question. Maybe finding the partition is very difficult. And in fact, finding the partition, there's evidence that it's probably NP hard for sure, right? So that's all right. So now it turns out that this theorem of Erberg, I mean, I already mentioned here, first of all, that you can prove the center point theorem, the existence of a center point on the data is actually follows from Erberg's theorem, because the point where all the colors intersect is actually one center point, which is remarkable, right? So in some sense, Erberg has found another way to demonstrate that center points must exist. Okay, so that's one application already of Erberg theorem. But let me tell you more applications of Erberg's theorem to data. So again, I'm talking about supervised learning here, but I'm going to talk about multi-class classification in data, right? So in this case, maybe you have photographs of M people. So for example, here you can see there's several photographs of the same people, where I'm taking photographs of these people in different situations. Like this lady here is smiling or without glasses, and this guy is smiling or just whistling, etc. Right? And so in some sense, what we are trying to do is to extend the classical two-color case to understand what happens when you try to classify with many colors. And in this case, when you have many colors, one of the most popular models to do supervised learning is logistic regression. So, I mean, we have, of course, k-means and logistic regression. And I just want to remind very quickly people that this is a classical model we teach on students. So you have n observations, and we have, let's say, labels, right? It's a supervised learning. So you have labels x, y, I that tell you the m different types of data that you can have. And so the model that people use is this famous model that you have a formula, this is the logistic formula, that will predict the probability that the data xi receives the label yi given equal to cs given the data, the existing data, right? The data you have proposed. And so we have some logistic, some regression coefficients. We normally run this regression. It's an optimization problem we need to solve, like in machine learning we always do. And what is the objective function? So what is the classifier, the loss function that we want to, the maximum likelihood estimator, right? So you want to, in the case of logistic regression, we want to maximize the log likelihood, which is, I just wrote here for you. So we want to maximize these. Remember, the xi prime are the data points. You have many data points, pictures of people, animals, etc. And then you have the regression coefficients here. You want to maximize this quantity. Okay, so but there is a very natural question that statisticians for many years did not realize was a problem. And I think many people in data science often do not realize it's a big deal. This optimization problem does not always have a solution, right? Or it doesn't have a maximum, or it doesn't have a unique solution, right? So that's an issue that you have to consider here. So in fact, in the 1980s, several statisticians published papers saying that, well, here's an example where the MLE does not exist. So the maximum likelihood estimator does not exist. And this is a big deal, right? Because you're running some regression or some classification on this data set, and you're getting garbage. You're getting nonsense, right? Essentially. So, but it turns out that already in the late 1980s, beginning of the 90s, people realized that for this problem of multi-class logistic regression, the existence of the MLE is exactly the case where there's a pairwise overlap of the data points. So in other words, you want to have actual overlap of the convex halls of the data, right? So if you think of your data points as points in d-dimensional space, you know, d is the number of features of your data, of course. You have actually this situation. Okay, so if that's enough. So if you have a pairwise overlap of the data, then that's enough. So the question then, the practical question is, okay, great. So how much training data do I need before I can be sure with high probability that the MLE exists? Because then I can be with high probability be sure that if I run my optimization problem, I'm not going to get garbage, right? Is the problem clear? Is the problem clear? Okay. Very good. So, okay. So let's look at the case of just two colors, because I think that's an important special case that you should understand. So again, so what's the situation? So you're sampling endpoints at random from a continuous probability distribution, okay? So, and now let's say that you color your points red and blue with probability 1/2. So you just flip a coin and you color your points red and blue, okay? So so then again, the question that I'm asking in this case is, what's the probability that the convex hull of the red points intersects the convex hull of the blue points? And how many points do I need before this happens, right? That's the question. And in 1964, this electrical engineer needed to exactly this to answer this question. And so Thomas Cover found an answer, an exact answer actually, for two colors and the uniform. So remember here, you're coloring the points with probability 1/2. I mean, it's uniform probability 1/2. The red or blue happen. So I only have two colors so far. So this is, in some sense, it tells you that if you have the probability that the 2 points, that the two colors intersect, if you pick n, I mean, n is the number of points you're sampling, d is the dimension of the data set. So it grows like this. So it turns out that this goes to 1 as n goes to infinity, right? And you can use this. This is an exact formula. This is an exact formula. But you can actually, using this exact formula, you can predict how many samples you need. I mean, there's a bound that you can recover. So in some sense, this is the beginning of the answering the question that I showed you before, right? This is this question for the case of two colors. For the case of two colors, okay. Is the cover theorem clear? Okay. Now, of course, in applications, in real life applications, we don't have independent label coloring, right? Maybe there's a dependence on the label and the data, right? I mean, that's most likely to happen. You know, that is going to be red with high probability if some features in the data are true. So we can try to answer the question: what happens with when the data is the labels are not independent of the data, right? This problem is more difficult, but it turns out that in 2019, the famous statistician Emmanuel Candès and his former student Sur, they proved that there's a similar phase transition. I mean, that essentially there's a size of the data that you can sample, but this time you need to parameterize. I mean, it's not just going to depend on n. It's not going to depend just on n, but it's going to depend on some. Essentially, it's two dimensional, but then you need to look at also actually at the at the regression coefficients of the data itself. So it's more complicated. The answer is more complicated, but they can give an answer in this case as well. So that's when we came in. I mean, actually, we started looking at this problem in 2000, at the end of 2019, beginning of 2020, and the question we wanted to answer is what happens when the color classes, you have not just two color classes, but you have many color classes, okay?
Can I ask a question? So Cover's theorem, does it imply also that it does not depend on your probability distribution, like for any?
So in the result of, in the result of Candes and Sur, you have some conditions on the probability distribution that it will depend a little bit on the probability distribution, but the probability distribution comes is given in terms of the xi.
Yeah, but in the previous slide for the Cover's
in the previous slide,
there's no dependence.
It doesn't depend on the. Yes, you're right. Thank you very much for that question. It does not depend on the how you pick the points, right? It's just how you color the points. Thank you. Yes.
So it's kind of uniform with respect to all, but you need them to be continuous.
Exactly. Just the only thing you need to know is that the probability distribution you're sampling from is continuous. Thank you. Yes, that's a great point. Thank you. And in some sense, the message is, thanks for Sergey's question, is that to understand this, even in this case, you need to look at the probability of coloring, right? The coloring probabilities. And so again, so in 2020, we started looking at this problem of what happens with more than two colors, right? What happens with more than two colors is a very natural question. And we tried to answer this question for the case of uniform coloring, right? So we are going to go back to this assumption on the, so we assume exactly the same. So we have a continuous probability distribution from where you sample the points, but you are coloring the points with probability 1 over m, so, you know, or with some probability that depends uniformly on the what color you. So all the probability that you get red, blue, yellow, green is the same, right? It's kind of, you have some uniformity on the coloring. So we are trying to generalize Cover's theorem in some sense. We try to generalize Cover's theorem, and let me show you what we got. So again, so this is the theorem. We assume that it's a continuous probability distribution. Our theorem depends that it's balanced. What does balance mean? It means that there is a point from which the probability distribution is symmetric. You can find a point in the probability distribution where the measure around on one side of the, if you pick a hyperplane, you leave exactly the same volume on one side or the other. So there's a kind of a center of symmetry on this probability distribution. We don't think this is necessary eventually, but our proofs depend on this. Okay. So what's the theorem? So we have again m labeled data points, and so now every color, I mean, every color is probability 1 over m, not 1/2, but probability 1 over m. And how many points do you need to sample to be sure with high probability? So what we observe is that if f of m is the size of the sampling that you're doing, right? You're sampling these points from this, and then you color them uniformly. And your size of the sample is bigger than this denominator that you see here. So it's more than m log 2 of m log of m. So you have sufficiently many points. And there is a factor of the dimension that I'm hiding here. Okay, there's a multiple of d. There's a constant, there's a multiple of d, a power of d. So in some sense, this term is in fixed dimension d. Okay, so in some sense, I'm stating the term in fixed dimension d. So in some sense, you should think that if you're in dimension d, you're sampling a constant times these many points, and this will be enough that to have with high probability that there will be an overlap. But notice that this time I get a two-Erberg theorem. So that means that all the data points will overlap. It's not a pairwise intersection, which is very, very different from what is necessary in statistics, right? In statistics, they just need that every two colors overlap. Here, I'm making sure that every color overlaps, which is giving you that every pair of colors overlap. Okay? But we can prove that in that situation, then you can guarantee that the maximum likelihood estimator exists. right? Yeah, so again, so let's just rephrasing everything that I said. In this uniform probability model, you know, as you let the number of points grow bigger, faster than this in dimension D, fixed dimension D, you get that you're going to have a 12-Erg intersection, right? You're going to have 12-Erg. So 12-Erg becomes easy to obtain randomly if you do random coloring, which is kind of surprising maybe, because it was so difficult to find it in the previous original theorem, you see? So we have proved an asymptotic 12-Erg theorem, but it's randomized, right? It's randomized, where you're coloring the points with probability 1/m. So that's a, you know, of a different reason, but then you can be sure that your maximum likelihood estimator will be okay. Okay, let me stop here for questions or for comments or. Okay, so very good. So yeah, I'm not gonna talk about the one case that we just wrote a paper that I really invite you to think about this paper. I'm just gonna tell you about this paper. It's on the archive. You can download it, where we look at this in one dimension. So you might say, well, Jesus, this is not interesting in one dimension. No, it is super interesting in one dimension, actually. And there's a lot of fascinating questions of combinatorial probability that one can ask here. So imagine that every so often a new bird comes. So maybe in California we have geese, or we have these sparrows, you know. So you go out and you watch birds. You go watch birds. So for example, imagine that somebody tells you that there's m types of birds. What's the probability that after, you know, n sites you're going to have seen all the m types of birds? So how many times do you need to sample, go watching birds before you see all the birds? That's a very famous problem in probability theory. I mean, I'm sure some of you have heard this problem in the coupon collector. The name is the coupon collector problem, right? Now, let me generalize this problem. Or make it more difficult. Is there a time in the year where I'm more likely to see all the birds? When am I more likely to see all the birds in a time interval, right? And we can answer these types of questions, but again, the type of probability distribution that the birds follow, right, is gonna influence the answer. And even the coupon collector, we do not know the answer for very difficult probability distributions. So it's very beautiful. There's very important mathematics going on here. And there's topology. You will see there's topology coming on. So are there any questions about this before I move to the more topological side? I mean, combinatorial topology, of course. Okay. So let me change to another famous algorithm in data science that we teach students in our first year class on data science. And that's the k-means algorithm. So there's many versions of k-means. But let me just very quickly kind of remind you of that. So you have data sets, in this case, these black points that you see, the black triangles that you see on the left. And then you start with some initial classification. You said, okay, there's 3 types of colors, or 3 types of data points, you know, and then you classify them into 3 parts. So maybe you do this classification, you put the red diamonds, the blue, what's it called, the plus signs, and then you have the black points, and then you compute the center points. Right? There's a center point, or the mean of this separation, and then you start changing the points. You're moving the black points to the blue points to the red points, depending on what is the closest center point. So for example, here I move this blue point. So this blue point became black because it's closer to the center point that I had. So, and I iterate this process when I update the certain center points, right? I move points around on different classes, and then I update the center points. Okay, that's the famous k-means algorithm in 5 seconds. Now, it's super popular. Everybody uses k-means or Gaussian. I mean, there's variations in with Gaussian measures too, right? Where you first do Gaussian, you feed some Gaussians, like when you have a, what is it called? It's a Gaussian mixture. When you have Gaussian mixtures, similar algorithms exist. But what people know in practice, and this is what is fascinating, in practice we know that the choice of the initial cluster will influence the number of iterations that it's going to take for you to finish, right? So that's my point. Yeah, so the problem is that the k-means is not, it doesn't necessarily go to a global optimal solution, but it might get stuck in a local optimal solution, right? And the answer depends on the initial partitions, right? You make a choice, maybe random choice, and you're going to get a different answer, okay? So there's a very natural question that people would like to understand. How can we understand what's the best partition? What's the best initial partition? How can we choose that? And try to, for example, make an initial partition that is going to take me faster to the global optimum, no? Or, for example, how can I identify the worst possible partitions? So maybe you know, Thomas tells me, hey, Jesus, I make my partition, I always seem to get the same answer. Why is that in your data? How can that happen in your data, right? So that's also a very natural question. My data might behave differently than your data, right? So that's try to understand this. And the answer is combinatorial topology, but it's not topological, it's not persistence homology. I want to show you there's different types of topology that are going to happen here that I don't think people know, are aware that are possible, okay? So are you ready? Is the question clear? I'm going to start moving now to a different topic in the last 15 minutes of my talk. So I want a new way to generate simplicial complexes from the data, and I'm not going to use TDA. I'm not going to use TDA. I'm going to use something different, but I'm going to borrow one idea from topological data analysis, which comes already from persistence homology, of course. So what I do is remember that if I have a family of convex sets, for example, here I have a family of circles, of disks, and I can compute a simplicial complex called the nerve of the data, right? Which is the simplicial complex, which you have one vertex for every convex set, and then you intersect. You put an edge if the two convex sets intersect. You put a triangle if three convex sets intersect, etc. So you put an I-dimensional face if I+1 convex sets intersect. So in this example, you can see, for example, here, these two circles intersect, so you put an edge, or these three circles intersect, and so I put a triangle, right? And I get this simplicial complex, okay? Now, all of you that I'm sure have seen persistence homology, you know that I use this, you know, the RIP complex and all this, you know, I start looking at these balls of radius something, I'm not gonna do that. I'm not gonna do that. So for me, the nerve complex is gonna come by looking at partitions. It's a different combinatorial information. So what's the partition? So again, so you have the data, and you can take the data set and just subdivide the data into different sets, you know, just partition, disjoint sets. Yeah. And I'm showing you some examples here. I mean, so here I have my original data, and I just partition into the most stupid way. Every point, I mean, every point except these two blue points are just on their own, right? They are singletons, right? So the partition has how many? It has one. Oops, something happened. Can you still hear me? Yeah.
Yeah,
anyway.
I hear you. Yep.
Okay. Yeah. So here I have nine parts of the partition, right? Nine subsets of the partition, and here on the other hand, in the middle, you see that I have just two parts because I color everything yellow and just two blue and blue, and here I have.
There's 1 point inside, so there are 3 parts for me.
Yes. Actually, yes. Let's say that that's a different color. Yes. Now, I was meant to put this red too, but yes, let's say, or here, let's say, if you think that this is a the same color. These are yellow, red, and blue, right? There's only 3 colors. There's only 3 parts. And what the message is that those are the family of convex sets, and I use that to construct the famous nerve complex. That's exactly what I do. I use the data, I partition the data, and that's what I do to induce a complex, a nerve complex. I wanted to show you this example. Let's see if I have another example. No, I didn't bring that example. Okay, well, it's okay. Yeah, so let's look at this data. These are points in the line, Sorry that some things are in Spanish. I hope you don't mind. So you see tres colores here means three colors in Spanish, and puntos means points, right? So here's what's happening. I'm coloring the points 4, 5, 6, 7, etc., all the way to 17 points. I'm coloring the points randomly with 3 colors. And then I look at the complex that I get by the partition, right? Because when I color the points, I get a partition, and I get different simplicial complexes. For example, how many times do I get this complex that is just every color intersects every color? Well, by the theorem of Erberg that I show you before, it's getting more and more likely. You see, the probability of getting that is getting to be almost 1. It goes to 1 by the theorem I showed you before, right? But you see, in dimension 1, you can ask the following question if you are a little bit topological and combinatorial. What are the possible complexes that can happen, right? What complexes can happen with the data when I partition the data, or when I run k-means? When I'm running k-means, I'm partitioning the data in many different ways. What are the possible simplicial complexes that can happen? That's the question we are interested here. And again, in dimension 1, we can answer that question because those are exactly coming from interval graphs. This is classical work in graph theory. And you can only get interval graphs that are chordal, are perfect graphs. So there's special kinds of graphs. As the simplicial complex is determined by the graph in this case. Dimension 1 is completely solved. So it becomes very interesting what happens in higher dimensions, because especially data in dimension higher than 1 is more common, right? Okay, so again, so the natural question is, for a given data set, when I run all possible partitions into M classes, what are the possible simplicial complexes that can happen? That's a very important question. And maybe some complexes happen again and again and again and again, and they happen when I have a lot of data, So maybe your biology people will tell you, oh, I start to see this complex. Is this an interesting information? The answer may be no, because remember, okay, so in the case of Erberg, okay, I didn't put it here, but Erberg tells you that when you have a lot of data, you must see with high probability that every color intersects. So there has to be some overlap, you see, at least in the case when you have uniform coloring, right? So in some sense, what we want to know is that, are there other complexes like in Erberg, where every color intersects? So that's the simplex. You see, the complex, the nerve complex that you get is the simplex, because every color intersects. So I can ask the question, are there complexes that always appear with high probability, or that with positive probability when I have a lot of data? So it's not a matter of what type of data you have, it's because you have too much data, right? You start seeing things that it's just natural to see them because you have a lot of data. Okay, I'm gonna illustrate this with this data set. I want to think about this data set. I love this data set because it's very small. It has what, 8 points. These are the coordinates of the points that you see here. I plotted them here. This is the set of points. Now, I can partition this into 4 colors, and I will never get this simplicial complex that you see here, right? So in other words, I can bet my house that you will never partition this set of colors, this set of points into 4 categories, into 4 classes, and that the overlap that you're going to get is exactly like you see here. There's the simplicial complex that tells you the overlap of the classes is exactly this line segment. Is the problem clear? I mean, is the statement clear? Yeah. But this is the amazing thing. Once you put a point number 9, you add one more point anywhere you put it, I will be able to find partitions of this like this. Okay. So you see, there's an asymptotic phenomenon on data. When you have too much data, some mathematical structures have to appear. So when you do classification of the data, they will appear. Yeah. So, and that's a little bit like a Ramsey type theorem. When you have a lot of data, something happens. Like in Ramsey theorem, when you have a lot of points in a graph, some structure appears. So we like to think that our theorem is it's like a Ramsey theorem about large amounts of data. Yeah. So that again, so if you have a point number 9, you're going to find exactly that the partition complex, right? The simplicial complex that I get by the classification of the data is giving you this simplicial complex. Notice that this has nothing to do with TDA, right? I mean, we use the same basic concept, but it's not using the TDA, the RIP complex. Okay, so yeah, again, so Erberg's theorem, remember, is essentially saying that when you have a lot of data, you're going to find a simplicial complex that is it's a simplex, right? Every color intersects. So that means that the simplicial complex is going to be a simplex. So the n-1 simplex appears when you have sufficiently many points. Those type of simplices I call omnipresent because, again, as soon as you have a lot of data, it doesn't matter what type of data you have, you're going to see those complexes in the partition. You're going to see those complexes in the k-means algorithm when you look at the different partitions. Yeah. Okay, so what are there other omnipresent simplicial complexes? And probably you guess in the last 2 minutes, 3 minutes, let me tell you the theorem. Oh, by the way, the type of data you use is important. Here is an example of a simplicial complex. It's a one-dimensional simplicial complex. It's this graph that you see here. That if you put if you put your points in convex position, so your data comes from a circle. So let's say that you're sampling data from a manifold that has a circular shape, right? Then no matter how many points you sample, you will never see this object, right? So that's why in the theorem, so when I say omnipresent, I mean that generic data. So the data is in general position. I mean, it's let's say random data, right? So there's a little bit it doesn't follow necessarily some manifold of sorts, right? Anyway, yeah. Okay, here is the theorem. So you have a data that is generic. So you sample sufficiently many points, and you will actually see not just a simplex like in the case of Erberg, but you will see trees, any tree that you want with m vertices, or any cycle with m vertices. And that's happening like in Erberg theorem as soon as you have sufficiently many points. And it turns out that we prove this using Ramsey numbers. So if you have the size of the sample surpasses the Ramsey number, then you're going to see this phenomenon happening, that you're going to partition the data in any type of tree. So again, the message is that if some people have data and they have a lot of data and they say, hey, you know, I was running the k-means algorithm and I see a lot of trees happening. Is this normal? Is this, you know, is this something to be scared about? You can tell them, well, this is just the fact that you have a lot of data. So when you partition into m parts, you are supposed to see all the trees. You're supposed to see them as part of running the randomness of the k-means algorithm. Okay, so I have 23 seconds, or so, no, sorry, I still have 5 minutes, but I wanted to stop for questions. And yeah, so we have the same result for trees and cycles. But again, if your data comes in a specific shape, you might not see some simplicial complexes, right? That's what I was showing you with this example. So you will see all the trees. You will get to see all the trees, but you will never get to see this simplicial complex if you sample the data on a circle. That's kind of the message here. Okay, so let me stop very soon, and I will say a few things to conclude that are not in the slide. So yeah, I hope I convinced you that every area of mathematics, in this case, discrete geometry, can be helpful to analyze machine learning questions. I only was talking today about essentially size of samples. I was talking about data classification on the supervised learning. But there are other areas like, I'm sure, I mean, we heard from the talk of Henry how representation theory should really be used more. And there are a lot of opportunities. Of course, to me, one thing that I didn't tell you today, and I will use the last, since I have still 5 minutes according with my watch, and is that you can also use the machine learning to try to understand data coming from pure mathematics. We have been trying to do that mostly around polyhedral geometry. So my group has been working a lot on trying to classify polyhedra by certain categories. For example, we have been interested on problems of the diameter of polyhedra, so the number of the size of the graph of polyhedra. That's one thing we have been doing. Another thing that we have lately is trying to understand problems on lattice points as well. I know that the group of Alex has done a lot of work on that as well. Anyway, so let me stop here to give people a chance to ask questions or comments. Thank you so much for your attention.